Now we're going to look at examples of Cayley tables for quotient groups. So I want to do some examples of factor groups or quotient groups. Here we're going to work with the dihedral group. And instead of the full rotation group, let's work with the cyclic subgroup generated by r squared. So it contains e and r squared. Remember, angle brackets, element is a set, not an element. So this is a subgroup. Now remember, D4 is the dihedral group. Here are the elements of D4. Here are the four rotations, 90 degrees, 180 degrees, 270. And here are the four reflections. Here are the relations in the group again. And we're talking about the symmetry group with a square. This subgroup, r squared is a 180 degree rotation. This subgroup has order 2. The full group has order 8. And so by Lagrange's theorem, the number of cosets is 4. But I want to do better than that. We want to actually construct the Cayley table. So my goal here is to construct the Cayley table for G mod H. And that's going to take a lot more work. And why does that take more work? Because, well, you need to be able to list all the coset, or all four cosets. Here they are, actually. I went ahead and did it for you. Clearly, there's the subgroup itself. Then it's not too hard to see that if you multiply r by the subgroup, you're going to get r times e is r times r squared is r cubed. Likewise, if you multiply on the right by r, you get the same thing. That takes care of four of the elements, the four rotations. So then there's 4 elements left. Multiply the subgroup by s to get another coset. That gives you s and sr squared. Likewise, if you multiply on the right by s, you will get r squared s, but by the properties of the group, r squared s is r to the negative 2s, but r to the negative 2 is r to the 2. So you're going to get sr squared again. So these two cosets are in fact equal. Why am I doing this calculation? Because we actually do need to check that H is normal in G. We're not just going to assume it. So I'm calculating cosets, and I'm finding left cosets and calculating the corresponding right cosets and checking that they're equal as we go along. And so I have 3 cosets so far. I've underlined s and sr squared. What's left? These 2 elements. SR would be a good choice of coset representative. That's the remaining 4th coset. Congratulations, by process of elimination, it has to be the remaining right coset as well. And so, yes, this is a normal subgroup. And these are 4 coset representatives. So we've accomplished step 1, constructing a complete set of coset representatives, and step 2, proving that H is normal in G, using the left coset equals right coset definition. So the final step is to actually create the Cayley table. So here is the Cayley table. Again, remember, angle brackets r squared is a subgroup. It's H. So each of these elements is of the form G times A, capital H. So it is, in fact, a coset. That just takes getting used to when you're working with a cyclic subgroup. And so this is what we're looking at. The majority of the challenge in filling this table in is I want to make sure, usually the challenge is that you want your answers or your table, since I've chosen these as my coset representatives, I want all my entries to look like these four. In other words, I don't want to see an SRS R squared. I want to be able to see the answers in terms of the four chosen coset representatives we've chosen. And in practical applications, that's actually the hardest part about working with quotient groups. So of course this is the identity coset, and so multiplying by it gives you everything back in both directions. And so the first column and first row are easy to calculate. So then you have the second row. What happens when you multiply by r? R times the identity is r times the r is r squared. Since r squared is already in this coset, you just get the identity coset back. R times s is actually rs. But what is rs? Well, it's SR inverse, right? Which is SR cubed. Oh yeah, I have it down here. And if you check our list of cosets, that was an element in the last coset. And so that is why we have SR here. So the first answer I could have put RS here, but it's best to rewrite the answer so that it actually has one of the four chosen elements, either nothing, R, S, or SR. So we have SR here. Now what is R times SR? Well, you do the properties, group properties, and you write R times SR as R times R inverse times S. Well, the R inverses cancel and you just get S. So R times gives you S. So that's 2 rows down. Multiplying through by S gives you S. S times R is SR. S times S is S squared, that's the identity. S times SR is S squared R. S squared is the identity, so you just get R. Finally, multiplying by SR. SR squared, since R squared is already in the coset, you can move it in, so you just have the S remaining. SRS, I have the calculation here. It simplifies to R cubed, which refactors as R times R squared. So it's just R. Finally, SR squared, since SR is a reflection, it has order 2. So if you do all the calculations, you get this Cayley table. And you discover that you get the identity down the diagonal. It's actually commutative. The product of any two non-identity elements is the third non-identity element. This is just C2 times C2. This is the symmetry group of the rectangle all over again. So this example is harder than the ones you see in the book, so I recommend looking at the ones in the book as well. I chose it because often the examples you find are usually simple cyclic groups, and I thought it was nice to have one that's at least slightly more complicated. As an example of a simpler cyclic group type example, let G be Z mod 12Z, and let H be the cyclic subgroup generated by 4. Well, then you got 0, 4, 8. Well, 12 is equal to 0 mod 12, and so the cyclic subgroup is just these 3 elements. Is H a normal subgroup in G? Well, yes. Whenever G is an abelian group, every subgroup is a normal subgroup. Why? Because if you look at this conjugation condition, G inverse times HG is equal to G inverse times GH, because H and G commute. And G inverse times G cancels, and you have H. Or equivalently, left cosets are equal to right cosets because little g times little h is equal to little h times little g. You have commutativity, so it's much stronger than just normal. So whenever you're working with abelian groups, checking whether or not a subgroup is normal is unnecessary. It's automatic. All right then, H is a subgroup containing 3 elements. G has 12. G mod H must have 4 elements. If I want to write down the Cayley table then, I need 4 cosets. Here's an example of a coset. 1 plus this 4 is going to be 1, 5, 9. And it's not too hard to see. These should be my 4 cosets. 1, 2, 3. This has 1, 5, 9. The next one should have 2, 6, 10. And the next one should have 3, 7, and 11 as its elements. And then here is the addition table. So the identity coset does what it's supposed to do. Now if I add 1 to 1, I just keep, or adding 1 to everything, I just keep increasing it by 1, with the exception that I know 3 plus 1 is 4. And since 4 is in my subgroup, 4 plus the subgroup is the subgroup. So this is something that's always worth noting. Whenever you end up with an element that lies in your coset or in the subgroup, then you actually have the subgroup coset, or the identity coset. Which tells you, of course, 3 and 4 are inverses in this quotient group. Which makes you go, wait a minute, they weren't inverses before. Why are they inverses now? Because this coset has 11 as an element, as another representative, and 11 and 1 were inverses before. So here's this inverse. So that shouldn't be the cause of confusion. 2. For this row, I'm adding 2 to everything. And 2 plus 2 is 4, which is 0, which is in this subgroup. And 2 plus 3 is 5, which is 1 plus 4, so I can get a remainder of 1. Here again, the inverse of 2 was 10, and 2 and 10 are both in this coset. Similarly, the inverse of 3 was 9. 9 was in this coset, so I expect 3 plus 1 to be 4, and I see that's what happens. So here I'm adding 3 to everything. And if you actually look at the addition operation, you see that what I'm doing is I'm adding a plus b, and I'm computing the remainder mod 4. And that's not too hard to see why. It's because whenever I end up with a multiple of 4, the multiple of 4 corresponds to another element in the subgroup. Right? So when I had 5, for instance, here, 5 was in this coset, so I could replace 5 plus 4 with 1 plus 4. But that does mean that it looks like my actual table is actually just integer arithmetic mod 4.